Okay, I was going to talk about how to rank variables in order of their importance for prediction. But before that, I think I will spend a few minutes talking about missing data. So it's not in my slides, but so I had mentioned that there are a lot of methods, machine learning methods, but they are not they're not equipped to handle missing data. But people use all these methods, and you wonder what they do. For the statistician, what we do is, if you really have to impute the missing data, there are imputation methods, which are basically regression methods. So if you have a data set and you have missing data, and you need to impute the missing value so that you can apply linear regression and neural network, what they do is they first initialize all the missing values with the column means or the column medians, so that now the data set is completed. And then they start with the first column, first variable, call it the dependent variable. And suppose all the variables are continuous so that we can use linear regression. Then you fit a linear regression model to the first column as the dependent variable, and all the other columns as independent variables, and just fit a linear regression, right? And the linear regression will give them predicted values. And they use the predicted values to replace initial missing value, imputed value. So they update the missing values in the first column. So the first column initially was filled with the means. The missing values were all means, and the second column was also the means and so forth. And they fit a linear regression, multiple linear regression. And so they get a y hat values, the predicted values, and they replace the missing values with the y hat. Now they move to the second column, x2. And repeat the same process with x2 as the y variable, right? So they use all the other variables except y2 to predict, except x2 to predict x2 using linear regression, for example. And once they get the linear regression model, they have the predicted values, and they replace the missing values in the x2 column with the y hat values. And they keep going that, and they iterate 5 times, maybe 20 times, okay? And so this is the idea here is sort of like the EM algorithm in statistics, but the EM algorithm really assumes that you iterate to infinity. In practice, nobody does that. So the hope is that if you keep iterating that, so theoretically, if you keep iterating that to infinity, you should be doing a pretty decent job, provided that the models you use to do the imputation at each step, linear regression, is the right model. Right? If that model is not linear, then you're imputing your y hats incorrectly. And then it may converge eventually at infinity, but it may converge to something else. Okay. But anyway, this is what statisticians do, which is if you think about it, it's kind of, it's kind of a lot of work for some problem that initially you don't think is so much work. So initially you think that you have a y column and it has missing values, and you need to impute the missing values so that you can get the average of the y column. So we have a special column called y, and all we want to do is to get the average of that column, right? The sample average to estimate some population mean. But because y has missing values, we need to replace the missing values with imputed values to get the column average. But then you find that what lengths we go to do that. In order to do that, you have to do it for every x column. All right, so the original problem is just the y column. If we impute the y column missing values properly, we're done. We don't really need any x's. All right. In fact, if the x's are totally independent of y, you don't really want to use the x's to try to predict the what imputed values are the missing values of y. But the idea is that maybe the x's have some information that can help you improve your imputations for y. But then you find that now you do. So if you have 500 x columns, the original job is just to impute the y column. Now, in order to do that, you impute 500 columns before you come back, to the original problem, right? So, and this kind of imputations conceptually seems reasonable, but in practice, they will be doomed for failure because of collinearity among x's. We all know that if there's multi-collinearity, linear regression can be unstable sometimes. There's no unique solution, right? So you quite often see these kind of things in real data. say sample survey data where they ask you like in the consumer expenditure data, how much you spend on food, how much you spend on entertainment, how much you spend on transportation and so forth. And there's a question that says, what is the total amount you spent last year, right? So technically that total is just totally is like exactly linearly dependent upon the previous. And sometimes they actually do this in good sample surveys. They actually have such questions as a way to check whether you're answering truthfully, because they want to weed out people who are not giving right answers. So they have some, check questions that you may not know. It may come down 2 pages down the line, which are similar to some question that you answered earlier. All right. So some of these things are actually intentional. And this is if all the columns are continuous, but if you have like binary columns 0, 1, like sex and so forth, male, female, then when you do that, you use logistic regression. Right? Logistic regression is even more unstable than linear regression because you can have what is called, I mentioned that quasi-complete separation, right? So it's like suppose we have x1, x2, and a y is 0, 1, right? So my data are either floating on top of on the ceiling here or on the floor. The ones on the ceiling, the zeros on the floor, and my x are the left, right, and front, back. Now, if somehow all the ones are in this corner of the room and all the zeros are in this corner of the room, right? Then your logistic regression curve will be like a waterfall. But if the ones can be totally separated from the zeros by an oblique plane, vertical plane, then you will have non-convergence. So if you do these kind of things, you will find that the software whatever software will stop working at some point, which is very frustrating. And that's what I found out when I spent the 2 summers at the Bureau of Labor Statistics trying to use this kind of method. There is, on the other hand, another method that actually industry uses a lot, which is very simple. Okay. What they do is they what is called a missing value indicator. So they have x1. Right, so they have x1 and x2 and so forth, right? So this may be 3, this is 5, and this is missing 6 and so forth, right? So they add a variable called x1 prime with the indicator that x1 is missing. Okay, so this will be 0. And this is 1, 1, 0. Okay, so they add that additional column. And then they will impute this with some number. And it turns out that it doesn't matter what you impute with. You can impute with the column mean for x1. You can impute with the median for x1, or you can impute with 0. Right? Even if there are no zeros actually in the real data in that column, right? The predicted value. So now if you have a y, right? So suppose we only have x1, then your model okay. So you fit that model, and the y hat will be independent of what number you put here. That's very interesting. On one hand, it is good if you worry that you impute the wrong number. You see, normally people don't have an x1 prime. If you ask people to impute, they don't know anything. They just impute with the mean, right? So they will impute the missing values with the mean for x1. You could impute that, but you can do better by adding another column, which is an indicator, right? And the good thing is that it doesn't matter what you impute, as long as it's a constant, the y-hat values will always be the same. Okay, why is that? Actually, the easiest way to see it is geometrically. So suppose here is x1 and here's y, right? So you have data. Okay, and then let me try this. So this is a missing, we call NA. So you have some numbers here. So you have 4 missing numbers. I cannot plot them in the original because I don't have the x coordinate, right? I don't have the x coordinate. So if you impute the mean will be here. They'll be like dragging these 4 numbers here, right? Okay. But if you look at the way I drew it, maybe that's not right because these 4 numbers seem to be higher than what this line shows. So if we ignore the missing values, I get a purple line, right? So, but if we drag these 4 numbers to, oh, I'm sorry, this one doesn't have a good color. So, unlike the previous room, the color here is not so good. So this is an example where the imputation of the mean is not good, right? I could change the example, for example, and say move them. Suppose I move them here, right? So that it looks like, you know, it looks like the reason they are missing is because maybe the registering instrument measuring x1 is out of bounds. So sometimes there are some instruments, right, that if it's too large, you just don't register anymore. So it could be like that. So then you should not be moving it to the mean, right? But what happens when you add an indicator variable? So now I'm going to change this picture from 2D to 3D. Right? So what happens is that this bunch of points, where will they be located now? They'll be located, this is a 1, this is the 0. They'll be located somewhere here. So I move it. So my x1 y space is on the blackboard. My x1 prime is coming out of the blackboard, right? Okay. So now I have a 3-dimensional space because I add 1 more dimension with x1 prime. And you can see, of course, I still have to you know, replace these numbers, right? Because in my model, I still have x1, right? But you can see that it doesn't matter what number I replace with, because how do I minimize the sum of squares for this thing, right? Without the missing values, if I only use this one, this one, this one, and so forth, the best fit is this purple line, right? So if you change that purple line, you're going to get a higher sum of squared residuals. But now, once I'm in 3D, I need to fit a plane, not a line, right? So to keep that minimum sum of squared residuals, I need to make that plane pivot around that line, right? I don't want that plane to be above or below that line. I want to slice exactly through that line because that's a line that minimizes sum of squared residuals for the observed points. But because that plane can pivot, I can pivot it until that plane cuts through the mean, because the mean minimizes sum of squares for those points, right? Okay, so what is the effect of this really is that if we fit this kind of model, it's equivalent to fitting 2 separate models. We fit 1 linear regression to the complete observations. That's this one. Then we just fit the average for the incomplete observations. So we separate them. It's like I'm trying to predict how much a person's income based on his wife's age of spouse, his wife's age. For those people who have income and age of spouse, I fit a linear regression. For those people who don't have age of spouse, I collect them and just predict the average. So anybody who doesn't have a spouse because he's not married, I can only use Y to predict because there's no X anymore, right? And algebraically, the reason it doesn't matter what you put here is because if you change that, then you just change your beta hat. But this thing is actually Y equals to beta 0 plus beta 1 prime x1 when, or maybe write it this way. X1 prime plus beta 1 double x1 minus x1 prime. Right? So x1 prime is 0, 1. So these two terms cannot both appear at the same time. If x1 prime is 1, then this term exists. If x1 prime is 0, then this term exists, right? So the beta 1 prime will change, but then this is also 0, 1, this x1 prime. So the beta 1 prime and the beta 2 will compensate for anything you change here, because let's call this a C, right? If you call this a C, then the C only appears here. Right? Because C only appears when x1 prime is 1. But when x1 prime is 1, this term disappears. Right? So, I mean, that's the reason why at first, the very first time I remember I heard of this, is that right? So on one hand, it's good news because it doesn't matter what you impute with, right? You don't have to worry that the mean is wrong. On the other hand, you can think that it's precisely because it doesn't matter. Maybe it's not so good. Don't you think so? Right? Because like this picture, I draw another picture. Right? And then we have, these are the missing values. Right? Maybe where these guys came from was that this point was originally here. 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 Right? In this case, they are randomly missing. So this point, if it was not missing, it would have been here perfectly on that straight line. But randomly was missing. So we just, separate them out as this column, right? So this is different from replacing these 4 points with a constant. You replace it with a constant, it's a wholesale move, right? So if you replace a wholesale move, and if the actual situation is like this, you will do a much worse job if you do a wholesale move, rather than move it back to where it came from, right? The trouble is here, we only have x1. There's no way to tell whether they were all the same x1 that caused them to be missing, or they were all, they're all proper x1 values, but just by a flip of a coin, we don't record them. We do record a y, and so they're all aligned at the side here, right? So this is but anyway, this method will be good. Actually, I don't think you can beat this method. If you only have y and x1, I don't know how you can think of improving the thing, because the four missing values, you only have the y, you have no x1. You don't know where to locate it, right? And so having putting a column, this missing value indicator column, I think it's definitely much better than not doing it and just replace that column with some constant, right? But in real data, we have x2, we have x 5,000. So you should be able to improve your imputation of x1, right? If you have other covariates that you think are relevant, okay? And this is where this method will not be so good, I think, in real applications with high dimensions, when there are other variables that can contribute information. Yes?
Do you just have x1 prime in that case, or you have x1 prime, x2 prime, x1 prime times x2 prime?
Oh, you want to put all the products. Okay. So, well, even without the products. So every time you have x, you have x prime. That already doubles the size of the number of columns, right? Now you're talking about cross products. If you have all kinds of cross products, what eventually will happen, as we saw earlier, is that each of them has an average. Yeah. So you have a lot of hundreds of mini models, depending on how many of these variables are missing. And then you don't get that kind of a sharing of information anymore. They're all, in fact, at one time with the guide software, I had implemented this, but then I realized what happens if we have just two observations that are missing. Now you use the average, right? And that variance may be very large. So, okay. But anyway, I think talking to people in industry, people who work on real data, when I ask them, they use all kinds of deep learning, I ask them, what do you do with missing data? They just look at me blank as if I'm stupid. Oh, we just do this. Yeah, you can get something. So suddenly it's easy, right? Easy to code. Only thing is you need a big enough amount of memory. But it will not work very well with a regression tree, guide or anything. Because this works well only if x1 and x1 prime are always together in the model. If you use lasso, for example, x1 prime may be dropped out and x1 is retained. Or x1 is dropped out, x1 prime is retained. Now it matters what you replace, whether it's a mean or some zero or something, right? So this works well, I think, for linear regression or logistic regression, but anything more sophisticated. So in a regression tree, we use one variable at a time to split. So if you now have x1 and x1 prime, the tree may split on x1 alone, in which case it will be quite important what you replace the missing values for x1 with, whether it's a mean or zero or whatever. Or it may split on x1 prime alone, which is not that terrible because it is x1 prime is actually an observed variable, 0, 1, right? It's an observed, although it's not very strongly, doesn't have a lot of strong information. Okay. So anyway, so I just mentioned this so that people don't think that I don't know that people who use deep learning and so forth, they probably just do this. Okay. But I don't think anybody has really. That was a paper I heard about in this last December during a conference. Somebody did some simple analysis for this kind of things, and they find sometimes it's good, well, most times it's good, sometimes it's not good, but they're all in the linear regression situation. Okay, so now let's go. Yeah. The white hat values don't matter.
Right, but if you just care about prediction, then sure you replace it by 0 and you've got some model and it's predicting well. So why do you care?
Yeah. So if all you want to do is predict, say predict a stock market, right? Probably is okay, but then you're predicting based on these averages alone, right? So you're not borrowing strength, so to speak. I mean, the phrase is borrowing strength from the other x variables. You're just adding this indicator variable. Okay. The indicator variable is basically to indicate to the computer that whatever I've replaced the missing values with is a special number because the indicator will flag that it's not a real observed number. So, okay, so yeah, so actually this is related to Varun's question somewhat. You say, if all you care about is prediction, why do you care about what you input with? Well, nowadays people are, I think, as far as prediction is concerned, the prediction problem, I think most people feel that they have sufficient tools to do predictions. I think most people find that real data are sufficiently noisy that there is no universally best model. Most models are quite reasonable. What people in AI are doing is try to interpret the models. That's where they want to understand, right? So even if you have the x1, x1 prime, x2, x2 prime, they want to know which x1 or x5 or x5000, which are the ones that are most important. So there's this concept of variable importance scoring. Okay, you want to score the importance of a variable. And there are many methods, right? And GUIDE has one, but before I tell you about how it works, I'll just show you what the scores show. So here we have 500 variables. I only show you in the top 25, otherwise you cannot read anything. The top scoring is amount of stock. We are trying to predict the amount of interest and dividends, right? So GUIDE says the most important, the longer the bar, the more important it is. So it's interesting because stock is 94% missing, but it is the most powerful predictor variable. Then CU tenure is whether you have paid off your house or you're still paying mortgage, right? Stock YRX is some discretized version of stocks. Then rent EQVX is how much your house will be worth if you were to rent it out. Then the age of the reference person is number 5. Per sort 64 is how many people in your family are above age 64, things like that, right? And I often find this informative, especially if I'm not an economist who is familiar with this data. But I bet even an economist who has had years of experience with this data, they will also find this interesting. They may want to see whether it agrees with their preconceived notions of the data or something that they never considered. So now, how do we measure the importance of a variable? If you think of linear regression, you may use the regression coefficients, right? You may use the T statistics, the standardized regression coefficients, to the absolute values to rank order the variables. But we all know that if there's, unless the X matrix in linear regression is orthogonal, unless everything is orthogonal, if you take out one variable or add another variable, the coefficient will change of any one of the remaining variables. Okay, so if you use the linear regression coefficient or the standardized version of it to rank order, then that ranking is dependent on the model you fit, right? You would like, maybe you would like something that is independent of the variable you fit, independent of the way you rank the variables. Another way that is independent is just to fit one variable at a time and look at the size of the coefficients, right? And that will give you a different kind of scoring, right? So it's a very slippery concept, but it is one that you would dearly wish there's a method to at least tell you. So you have 500 variables, or if you have a genomic data, you have 500,000 variables, 500,000 genes, right? You would really like if somebody tells you, just look at this 20, or just look at this 100, right? So maybe people will use multiple methods and see whether they agree or disagree, right? But they all depend on how the method is defined. So I'll just tell you how GUIDE does it. So you see, GUIDE is a regression tree. So at each node, it splits the variables. And we already know the way it chooses the variables to split a node is by a chi-square test, right? With a sort of a Wilson to the 30 sort of normalized chi-square. So with GUIDE, at a root node, we already know which is the best variable to split the node because we already have a ranking based on the chi-square values, right? But that's only at that point, okay? At that point, you may have a variable that is the best, but there may be a second best variable that is could be better if you split some more, right? So what I did with guide is I let guide grow a short tree because I don't want to spend a lot of time getting this variable important scores. Besides, when you go lower down the tree, you probably think those scores are probably less important, right? So I grow a 4-level tree, 4 split levels, and then at each node, I have a score for every variable. So at each node T, I have a score for each variable xi. W is just for Wilson, right? The Wilson Huberty. Now, and then, okay, so ignore this for now. I just get a weighted sum of these scores over these 4 levels of the splits, right? I weight it by square root of sample size. So I want the top earlier upper nodes to be more important, to contribute more, right? Then you can ask me why I use square root. I tried without a square root. I find this seems better, but this is just just a method. You could change the cube root if you want. And so this will maybe give me a some semblance of an importance scoring system, right? You cannot just look at the one node. So I think of this as the following. At each node, there is a number 1 variable, the best one, which will be chosen to split, and number 2, and so forth. So this is like the Olympic Games, right? So the root node may be 100 meters sprint. So that will be a gold medal winner, and so forth. After you split, maybe the next node is swimming 100 meters, right? And next one on the right may be cycling. So this variable importance score is like an Ironman competition. In an Ironman, you look at the person who finishes all 3, the total time. You run, you swim, you cycle, okay? And the one who gets that gold medal for the Ironman is the one who does the total in the shortest time. He may not win any of the individual events, okay? But in total, he's the fastest. So a variable importance score to me, and that's how I decided to measure it, is to use this method. Now, random forest, a lot of people use random forests. You may have heard random forest can give you importance scoring. What random forest does is the following. It grows a random forest, and then after the forest is grown, it puts its data down the trees, all right, to see how much error is committed. And then to see whether x1 is, what is the score for x1? It randomly permutes the values of x1 in the data and points down again, right? So the idea here is that if x1 is noise, it probably will not be selected in any of these trees if the algorithm is smart enough. So when you shuffle, x1 is never used in any of these trees, or at least minimally used. So the change in prediction error will be minimal. But if x1 is a very important predictor, okay, now you mess it up. Suddenly you find that your error rate shoots up a lot. So the idea of random forest importance scoring is to do this, is to shuffle each variable in turn, and then see how much the accuracy or error rate changes. The more it changes, the more important that variable. That's how random forest does it. And when you first think of it, it seems reasonable, right? It seems reasonable, except now what happens if I want to screw it up? I take the data, and x1 is very important, right? I copy x1 5 times. So now I have 6 copies of x1, and I grow a random forest. So suppose I only have one variable that's important, it's x1. Add 5 more copies. So random forest, if it's truly random, it will pick one of these 6 every time it's supposed to pick x1. Now, if you shuffle one of these columns, the impact may not be so great, right? So what people have found with random forest importance scoring is that if you have correlated variables, of course, the example I gave is extreme, the exact copies, but if they're correlated, then suddenly, even if all these variables that are correlated are important, they suddenly lose their importance by a lot just by the fact that they're correlated. Right? So this makes me wonder, and you can think about it yourself. Like I have 2 kidneys. Are kidneys important? Is this kidney important? Well, this kidney is correlated with that kidney. Right? If somebody needs a kidney transplant and I have 2 healthy kidneys, I can donate 1. Right? So in other words, because they're correlated, maybe they should be less important. Well, suddenly hair is, right? I have lots of hair. Okay, they're all correlated. I can give you some, and it doesn't hurt me. Right? So in that sense, maybe that's the way it should be. Maybe, you know, if variables are correlated, they should have less importance. So suppose I have x1, x2 up to x6, they're correlated. Each of them is individually much stronger than x7 individually. But because there are 6 of these guys, suddenly x7 becomes more important than any of this. Now, that also makes me somewhat feel uncomfortable, right? With guide, this will not happen because if x1 up to x6, they are exactly the same, the Wilson-Rayford score will be exactly the same. So even if you have thousands of copies of the same variable, they will return exactly the same importance score, right? They do not get diluted because they are correlated. Because each of them is individually assessed with a chi-square test, right? So if they're exactly the same, the chi-square is exactly the same. So anyway, I don't think that is the last word yet on this. I just want to mention that this is the guide method will ensure that redundancy does not wash out the importance of a variable, okay? But whether or not redundancy should wash out importance of a variable is a conceptual question that you may want to think about. But yes?
So what if they're not exactly the same, but they're slightly different, so that one of them has a higher score than the other?
Yeah.
So that one is always picked and the other one is never picked. Always you get that this one is very important, that one is completely useless, even though they're
If you're talking about the guide method or random forest method. The guide method, if one is a bit more important, the importance is measured by the chi-square test, right? So the chi-square test doesn't care about other variables. So if one is very important, next one is less important, then you should have a smaller chi-square value.
Yeah, it's only slightly. They're almost identical, but
right.
Because of slight randomness, one of them happens to have a
so you're saying by accident they get switched?
Yeah.
Well, if by accident they get switched, I don't worry too much because like here, well here, let's look at this too, right? Rank equivalent and age, they're almost the same, right? So as long as the bars are long enough, okay. You see, the thing is that another advantage of a graph like that is when you look at the tree, if you have 500 variables, you're not going to see all 500 variables represented in the tree. Variables that are highly correlated because they just miss, right? So it's like in the Olympic Games, right? Everybody knows that Usain Bolt was the fastest man for many years. Do you remember who was the silver medalist at any of the times? Nobody remembers that. They only remember the gold medal winner. But the silver medalist is also pretty fast. Okay, if not for Usain Bolt, he would be the gold medal winner. So, you know, I'm not too concerned about getting really the gold medalist versus a silver medalist, right? I don't want to mistake a gold medalist. I don't want to give it to an iron medalist and miss out the gold medalist. So yeah, there's always a chance that, but just by sheer virtue of the randomness of the data, right? You miss that. One way guide, there are 2 ways guide can sort of compensate a little bit. It is this graph, right? You see this graph, CU tenure doesn't appear in my tree. This graph tells you there are important variables. They're the silver medalists at every node. They got a silver medal, okay? And but in the terms of Ironman, CU tenure is actually pretty good, okay? So this graph will tell you that that the tree, in fact, that's a problem with the tree. The tree is too interpretable. People complain that other methods are not interpretable. The tree is just too interpretable. It's like candy. You see candy, you know you can just eat it, right? You're so, it just draws you into it. But the problem with that is that people conclude erroneously that the tree is unique, that that's the only model. The tree is a summary, like a histogram of the data. So like if you take a picture of me, right? You get a picture like a tree. But if I turn slightly, you take another picture, and it's still me, right? And if I turn enough, the two pictures will look quite different, but it's still me, right? So what Guide does is in the software, after it outputs the tree, it will tell you the best variable that was split, use to split the root node, the second, and so forth. And then you can tell Guide, use the second best, and it will give you another tree. And you can say use the third best. So it's like taking multiple pictures of me, right? And if you really want to get to know me, how I look like, you want to take multiple pictures. You don't want to just take one picture, right? Because if you take only picture like that, you may think that I have a tail. Actually, I don't have a tail, right? If I were an animal or cartoon character, you may think that maybe I don't have a tail, or maybe I have a tail. In order to do that, you would turn and take another picture, right? So the Guide or any regression tree method, the interesting thing, the funny thing is, because it's so interpretable, people will say, oh, I don't believe in this. I don't believe in this picture, okay? Because I know there are some variables that are important, but it doesn't appear in that picture, right? Well, it just got bumped out by another variable, okay? But in terms of prediction accuracy, it is decent, and it gives you a picture, right? Otherwise, you have no picture. Okay, so all right. So, but there is one thing that we have to be concerned with is this thing. You see, if we split it on sex, male or female, after that, even though we split this tree at 4 levels, after that, sex will never come out because all the males are on one side, the females are. So how do you accumulate that, right? So this formula here assumes that at every node, there's still, every variable still have some means to be used to split. But sometimes if you have a binary variable, you get zeros. So then this will not be a very good score, right? You penalize those that are very strong, they are split first, and then they don't contribute anymore because they're exhausted. Those variables, the information is exhausted. So it took me many years to do this. You see, one of the things when you propose a way to measure the importance scores, you want, again, this concept of unbiasedness. You want to make sure that if all the variables are independent of Y, they all have the same score, right? So how do you ensure that? Okay, the Wilson-Hilferty chi-square sort of ensures it to some extent because each of them is a chi-square. But then you have this problem when you have a binary variable, and once you split on it, then there's nothing left. You have to define something. You know, in this formula, this square root nt times w, that w has to be defined. I just defined it as 0, right? It still has to enter that, right? Okay. So what I do is, perhaps you will think it's now quite obvious. I just permute. So I randomly, so I have a data frame, I have a y column, and I have the x variables, and I want to predict y. So I take the data, and then I permute it 300 times. Each time I shuffle the y column. I keep the x columns fixed because I will keep their correlations. I don't destroy the correlations, right? I keep the y columns fixed. And each time I do the same process, I grow a tree with this permuted data, and I get the unadjusted. I call this unadjusted score. This is this score. This unadjusted score, right? I calculate that. So now I have 300 of them. All right, and I just average them. So if you have a binary variable whose unadjusted score is necessarily small because it can only be used once, the average will also be small. Then I divide by the average. I divide the unadjusted score from the real data and divide it by this average from the permutation. It's like a bias correction. Most of the time, people do bias correction by doing a subtraction. They subtract the bias. Okay, but here I divide by the mean, so it's like a bias adjustment, and this will make sure that I don't have to worry. Otherwise, there are a lot of things to worry. The chi-square approximation, first of all, is non-uniform, right? We already know that. So even if I don't have this problem with some variables being constant, right? I may still not get complete unbiasedness because I'm using chi-squares to get the scores, and those chi-square tables are not uniformly convergent, right? But once I do this adjustment, then the adjustment is like a second order correction. Okay, when I do this, it's like a second order correction. The first order correction is the chi-square. The chi-square really gives me a first order correction. And I will not need another correction if the chi-squares were all uniformly convergent. But because they are not, but it's still, you know, asymptotically they are correct. So it's a first order adjustment. Then I do a second order adjustment. Okay. So now, with this thing built into the software, now if you want to show that guide is not unbiased, what will you do? So I claim that guide will give you unbiased importance scores, and you want to prove to me that guide doesn't have that property. You will take my data and do exactly this. You will take the data and shuffle Y and show that if you do this many times, X1 seems to be on average having a higher score than X2 and so forth. But this won't happen because internally I did the adjustment already, right? So, okay. So, wow, I'm really, okay, there's a way also to get confidence intervals. I think I'll skip that. So I'll just, maybe since I only have a few minutes left, I'll spend the rest of the time to this lecture, next lecture, just showing you some applications. So this is an application to Poisson regression. If you use R, you know that there's a book that was published in 1992 called Statistical Models in S. Well, before R, there was S. S was a precursor of R, but S was written by some people who work for AT&T. And AT&T did not want to be sued. So AT&T would not give out this S software. Okay, not because of anything. They worried that if there's something wrong with the software, the company will be sued. So it's a defensive copyright protection. So as a result, some people outside of AT&T wrote a clone of S and became R. Okay, so until then, there was this paper, this book, which was the first book. The first book on S is a blue book, which I love to read. I mean, you can read it in a few days. It's just fantastic. And then this is called a white book, which shows you how to use functions like generalized linear models, GLM. Okay, so that was the first time when GLM became, you know, free and very easy to use. So the authors, Hasty is the guy in this book, Statistical Learning, right? Hasty, and Chambers was a big shot in AT&T. They were so proud of what they did with this GLM function. They gave this example in the book, and you can see how proud they are. They talk about this in the preface of the book, and they were really so proud of it. They didn't call the preface of the book preface. The preface is called appetizer. So you really, when you read that book, you are drooling. I mean, you know, you have to bring yourself back to 1992 or 1990 when software was very expensive and hard to use and so forth. And then you see, wow, this is, of course, at that time, it's still not free. It's still S, right? So they had this example to show you how powerful is the Poisson regression model. Nowadays, it's no big deal, right? So they had some data, 720 observations from a factorial design, it's a cross design. So 3 by 2 by 4 and by 10 by 3. So there are 5 variables, predictor variables. One is size of the opening. So this is soldering. So they are soldering computer circuit boards. So the amount of clearance around the mounting pad, there are 3 levels. There's the 3. And then there's solder amount of solder, thick and thin, the 2 levels. And mask, there are 4 levels and so forth, right? So this is a real experiment. And the response, the y variable is number of solder skips. Okay, if there's a skip, then what is this? Then it's a defect, right? You want it to be 0. So this is an unreplicated 5-factor experiment, which means that you cannot fit a full model with 5th-factor interactions because they will overfit. And even a model with 4-factor interactions, you can fit that, but it's very complicated. So these authors showed this model with this is the full 2nd-degree model. So they included all the main effects, linear terms, and 2-factor interactions, right? And you see that, my goodness, everything is significant, except maybe this one, right? So now if you're the consulting statistician, you'll be really super excited. Applied statisticians are really excited with small p-values. You go to tell the engineers, wow, there are a lot of interactions. What do you think the engineers will tell you? They'll say, we know, that's why we did this experiment. This experiment was done to understand the interactions. These engineers are trying to exploit the interactions. You know that as an engineer, you can get a better product not by putting in more costly materials, but by exploiting the interactions, the design, right? So if you do this, you have not really added new information to the engineers because they already know it. That's why they commissioned this experiment, and it may have been a costly experiment. Anyway, for us as statisticians, this table is actually not very useful. Still, I mean, we just know that there are a lot of interactions, but actually it's a nightmare. When you see so many interactions, you get a nightmare. How are you going to explain to the engineers? How are you going to explain to yourself, right? What is going on? So Chambers and Hastie, in their preface or in their appetizer chapter, they decided to include coefficients. So this table has no coefficients, right? This is like an analysis of variance table, just degrees of freedom and deviance. So they included 2-factor interactions. Now they have coefficients. So these are the main effects for masks, pad, and these are the 2-factor interactions, right? But there are too many 2-factor interactions. So they decided to take only 2-factor interactions involving the 3 largest main effects. Otherwise, there are too many 2-factor interactions. And they got these results. And this is a demonstration of how powerful is GLM software. But this is still very hard to interpret, right? What's going on? Well, you see, if there were no interactions, then it's easy. If there were no cross products, then we want to minimize the number of solder skips, right? Then the best mask would be, so there are 4 masks. There are 4 masks. One of them is set to 0. It's alphabetically first level. So the A1.5 is alphabetically first level. So that's set to 0. So this says that A1.5 mask would be better than any other of the other 3 because the other 3 have positive coefficients, right? The pad, right? The best pad is this one, W9, because it has the most negative. The set to 0 is 0, right? Panel, there's panel 1 and panel 2. It should be panel 1 because panel 1 is set to 0. And opening should be large. L is alphabetically before M, and large opening is set to 0, right? So you see, if there were no interactions, that's easy to interpret. So if you ask me what is optimal design, optimal combinations, I would say use A1.5 mask, use pad W9, use panel 1, and use a large opening. Finished. But there are interactions. Okay, so what do we do? Well, you can try to fit a guide model. And the guide model is huge because it's fitting piecewise constant. And this doesn't help you very much too. You can see all the interactions going on, right? First it's based on opening, then it's based on mask and solder type, thick or thin, and so forth, right? But what I can do is I tell guide to fit a piecewise main effects only model. That means in each node, I don't fit a constant, I fit a Poisson model, but with no interaction terms. Because I want something like this with no interaction terms. Okay, so I tell guide to do that. So guide grows a very big tree, gets pruned back, and then it got only 3 nodes. This is a node where you use thick solder. This is a node where you use thin solder and small opening, and this is a third. All right. Now I can show you 3 tables like this, one for each node, but without this. Okay. So now this is what it is. This is 1 node, and there are second and third. Right? And now you can see that for A1.5 mask is still set to 0. So for mask, the best mask is A1.5, still A1.5 for all 3 nodes, because A1.5 is set to 0. For opening, it is still large, because the large is set to 0. Right? For panel, it is still panel 1. And for paired, it is the one highlighted in yellow. So you see that actually the situation is very simple. Okay? It's very simple. There are interactions, but the interactions are explained by the tree. So the interactions are revealed this way. Say just take here, right? The coefficient for A1, A3 is 0.47 here, and 0.31 and 0.81. So it goes from 0.47 down to 0.31, goes up to 0.81. That's an interaction. That means the interaction occurs when the effect of one variable is modified by the effect of another variable. Here, there are 2 other variables, which is the thickness of the solder and the opening. Right? Depending on what are those values, the coefficient for mask A3 will change. And that's why you need cross product terms if you want to express the whole thing into one mathematical formula to these adjustments. But with the tree, you just partition the data. Okay, so so this is a sort of an alternative way to analyze the data. And you can actually write in equation form if you want. It's just a lot of indicators because of the branching. Right? I'm out of time, but I just want to show you the result here. So I'm plotting the fitted value, observed versus fitted values. These are the observed values. These are actual values. They are observed, right? This is the predicted values from the human gold standard, the experts. So if the humans can predict the data correctly, it's all on the 45-degree line. These 2 are machine learning solutions. Which one do you think fits the 45-degree line better? I think the middle one beats the humans, right? You see, the humans are straggling over here because they are fitting a quadratic model, basically a 2nd degree, right? So the 2nd degree model still has some stiffness, right? Whereas here I'm fitting a 1st degree model, but 3 1st degree models, right? So you can see that, I mean, this is one demonstration of how a machine learning algorithm can even beat human experts. The human experts made a lot of decisions. They decided to do a 2nd order model. They decided on which interaction terms to include in the 2nd order model. And this is the best they can do. The piecewise constant is actually not too bad. It's a bit more discrete because there are only so many y bar values. Right? Okay, so I'm sorry I went way over time. So next This Wednesday will be the last lecture. Right, so we'll run through a few more examples on Wednesday. Right, thanks for coming.